organizers asked me to sort of focus on performance and portability lessons with our code, which is called HACC, and I'll tell you more about HACC in a second. So the important thing to keep in mind with our code is that it's actually not written by many people. So there's a lot of stuff that we do that involves I/O and analysis and so on, and these things are actually almost as important as the main code itself. But out here, I only have the names of the people who are actually contributing to the main code development. So you can see it's a relatively small team. So most of the things I'm talking about today are basically going to be about how a small team needs to worry about writing code for next generation systems and current systems and so forth, with the idea of emphasizing performance and portability. Of course, these are diametrically opposed things, as you all know. So, and I don't think I need to emphasize this too much, but I want to make, thank you. Thanks. But I just want to make a point that there's nothing new in this business, right? We knew that we are going to be in trouble in 2004, but we just didn't realize it. And the problem simply is the fact that the clock rate, saturated around 2004, and which is why the particle physicists, as you heard from Tom, they were thinking things are going to go like that, but they did not, and so that's the problem. The second problem, which again is a real issue, is the fact that the memory per flops also hit this wall, because memory is expensive and takes a lot of silicon real estate. And in order to deal with all of these things, well, all we can do is produce more cores, and power then becomes the main constraint. And the point is to get this 30x performance gain by 2020. We want a system that doesn't consume too much power, say 20 megawatts per lot system. I mean, we are in a situation where power per socket is roughly constant. These machine designs are the way they are. So the only way out is more cores. And this is a bad thing from the scientist's perspective, because basically what we would like is a single super fast core with enormous amounts of memory, and that would be fine. But unfortunately, that's just simply not the case. And especially in these new designs, lots of the gains from the past, like microarchitecture gains, have been sacrificed. And so we have a very restricted memory access structure on these chips. So designing for performance is tricky. There's also an enormous machine balance sacrifice that has happened. In the 90s, there was this idea that all machines should be balanced in some sense. And there were various metrics for balance. And no one talks about those metrics anymore, because guess what? They are terrible, right? So the machines that you have here are now very different. And therefore, all our low-level code in some sense must be refactored, or rewritten. And this is, I think, a lot of people have been saying this. I just want to make this point. There's not an easy life ahead of us. So because this life is not easy, you should ask yourself the first question, which is, do I really want to get into this business of high-performance computing, or more specifically, supercomputing? So I want to emphasize that I am thinking about HPC always as supercomputing. And my definition of a supercomputer is a machine you cannot afford, okay? Because if you had access to it, in your lab or on your desk, it's not an HPC system. So that's the definition. So these things are very, very difficult to deal with. They're extremely large, and a lot of effort has to go in to get things to work. So why would you want to do this? Well, sometimes you have to make quantitative predictions for complex, highly nonlinear systems. This is the only thing you can do. Other times you have extremely complicated systems, and you want to understand what's going on in them, and pencil and paper can only take you so far. So you need essentially a computer to even explore what's in your equations, because you're not smart enough to understand what's in your equations. And this is, for example, our situation in the code that I'll describe. You also want to do system scale simulations, things that you just cannot do otherwise. For example, climate is a good example, right? I mean, we just can't say, all right, give me enough funding so I can create an alternative planet and check things out. It'd be nice, but there's not enough money. And other things involve large-scale inverse problems, where you often have to run a forward model many times just to solve a problem where, let's say, I can do the experiment, I have a model, but the model has many parameters, and I have to run the forward model many times compared to the experiment. So these are all things where you might want a supercomputer. The interesting thing about my field, or at least one of my fields anyway, is computational cosmology, is that we are faced with all of these problems, which is why we need a supercomputing code that is super fast and can run at full scale on all machines. Not just machines now, but machines decades in the future. That's the scale of our problem. So when you're asking this question about should I be programming on a supercomputer, you should ask yourself these questions about, okay, suppose you have very large simulations that are necessary. If it's just a matter of running one or two, it's not a big deal if the code doesn't run very fast. because if running it in a week or a day, that hardly matters. But if it's something you have to do repeatedly, then it's something that's very important. So high throughput is essential to you, then that's something to worry about. And then you have to think a lot about how to design simulation campaigns, for example. But that's something that's not really part of this talk. There's also this question of large-scale data-intensive applications, which, as you just heard from Tom, are becoming an interesting thing to do in future machines. So these are sort of the motivations. So let's assume for the moment that you have found a task for which you're motivated, and you say, all right, let's just put it on a supercomputer. Well, the important thing here is that sociology enters. There's a technical aspect to supercomputing and an equally important sociological aspect. And this depends really on the teams that are tackling a certain task. So most codes are written and maintained by small teams working near the limits of capability. By definition, if you're a small team, you're always in this situation, right? So there are no free cycles. No one has any time to do anything. You're always maxed out. So that makes life hard. So then you say, OK, great. Let's make sure that our problem is interesting to everybody. Well, first of all, that's not necessarily true, right? That your problem is interesting to everybody. Second, it may be interesting, but it may not be sufficiently interesting in the sense that enough for them to actually start coding. But let's suppose it is. Then you can often sometimes have a community code. Now, that's often very useful. The downside with a community code is there's a large inertia associated with it, because it's not easy to change standards, untangle lower-level pieces of code from high-level organization, find the people who have the expertise to help you with your module of this thing. And what happens if the new machine comes along and this doesn't work? Sorry, you're out of luck. So there are pluses and minuses to everything. One of the big problems that we have right now is that there's a lack of consistent programming model for scale-up, meaning it would be really, really nice if I could run a simulation of my code on a laptop in such a way that I simply said, oh, yeah, it's all going to work great. I just have to push it to the main machine, and everything would be fantastic. Unfortunately, we can't kind of do that right now. So as a result of all these difficulties that I outlined on the slides earlier about the computing architectures changing, people are getting extremely nervous, and at least some people are arguing about some sort of crisis, which I actually don't believe, right? So I think we will definitely go beyond this, because the vector to MPP transition, which some people here may be old enough to remember, was much, much worse. People had to take code that they've written for decades and throw it in the trash and write brand new code. Well, I don't think it hurt us. We actually became stronger as a result. The problem is that this transition needs to be staged, because there's not enough manpower to completely rewrite the code base. And I would argue that it's probably not a smart idea to go crazy and start rewriting a code base without staging it and being careful about how you're doing it. The one thing I do want to say is that there won't be any ready-made solutions. So if people expect the CS and applied math community to solve their problem for them, they're sadly mistaken. They are definitely going to help, but it's something we'll have to do for ourselves. Okay. So now let me just say, so these are sort of hard-earned lessons that I firmly believe in. On performance and portability, there are these just 2 slides. Now, of course, some people may disagree with me, and it's a question of what kind of hard knocks you've had in your life, right? What kind of experiences. So these are mine after 20 years of being abused by supercomputers. So one important is, are you sure you want brute speed, right? Because maybe you don't, like I said. Maybe you only need to run 1 or 2 simulations, and that's it. Sometimes the performance bottleneck isn't really the bottleneck. The bottleneck may well be that it takes you a few days to run the simulation, and then it takes you a month to do the visualization to understand what the heck happened in the simulation, in which case you don't really want to gain a factor of 2 in performance, right? So, and remember that, as I said, the machines are poorly balanced, so if you really want to optimize your performance, it might take you a long time. And so really the case often is that you don't really want to get very high performance, you just want to get a half-decent acceptable time to solution. And you should view this not just as one piece of a problem, but as the entire scientific thing that you're interested in. You should say, well, one of the things I have to do is run this code, but so what? What is the big scientific picture in which it fits? So that's a very important thing to keep in mind before you start writing any lines of code or modifying some piece of code. So the other important thing, step 1 in this, is that if you decide that finally, yes, performance is important, at least in some piece of the code, then you have to design it right at the very start. You will never get it afterwards. If you design some massive framework and say, oh, I'll fix the performance thing in the end, it just won't work. So optimizing gains are often minimal to non-existent once everything is sort of hard-coded in some way. So if performance is needed, you have to really understand the global science problem from the beginning. That's my strong opinion. And I will try to explain that as I discuss how our code is written, why that's so important and how the code was written. There is no replacement for domain knowledge. So the computer is a very blunt instrument, right? You have to just keep that in mind. So if you're smart, and then you have to amplify that intelligence by using the computer, not be lazy and say, the computer is fast enough, it's fine, right? It's kind of a trivial statement that's extremely important. So the factor of 2 rule is something that many of us understand very well, and I think I just want to explain this again. It's usually not worth it to go for the last factor of 2. So suppose you have a code and you've written a certain way, you understand it, you like it, its performance is acceptable, and people are coming and saying, hey, change MPI to something fancier and newer, you'll get a 30% advantage. My answer is do not do that. Okay? Only when the advantages become sufficient that it's worth it to do something that later on might really get you a big advantage, and fine, but don't go for things that are worse than a factor of 2. The other important thing about this is that obtaining performance, as you will see, is painful, and as you may have found out already. So you must design for the future. And designing for the future, again, there's a sociological aspect of designing for the future, is that we don't know what's going to happen in the future. But one thing we know is that things are going to be worse. Okay? So that's an important thing to keep in mind. So you must understand what is it that actually will remain that way, what can disappear. For example, there may be some extremely cool tool that's been written by somebody else for, let us say, profiling your code, and you become so reliant on it that when it disappears, you're like, now what? So it's extremely important not to become over-reliant on things you cannot control. I mean, to some extent, this is a part of life, but you just have to worry about all of these things. So the important thing about supercomputers are they're not your laptop. And it's not like, you can download something, it'll work. They're extremely painful. So you have to learn from experience. So if something bad happened the day before, chances are if you repeat the same thing, it'll be bad again, right? It's not going to get better. So I'm not going to here to give you a talk on the general sort of advice, which is pretty much obvious, and everyone knows this. So you want to do the on-chip and node optimization first. You have to make sure that when you want to scale up, you're not going to be communication bound. You have to minimize the number of performance hotspots in your code. This is all like, supercomputing 101, right? Data motion is, of course, super important. If your code is stuck with a lot of data motion, you're dead. You should give up. And you have to avoid lookups under any circumstances. One of the big problems I see people getting stuck in is the forest/tree syndrome, which is what happens is there's a big problem, but instead of working on a big problem, you say, oh, no, but I'll fix this other thing first. And that problem avoidance is something that's really crucial, and you have to make sure that you don't get stuck into that. You should think about things like sacrificing memory for speed. Now, I understand memory is at a premium, but data transport is even worse. So, and at least in our code, this is something that we've done, and we've taken memory hits sometimes at the level of factors of 2 to get the performance that we need. And there are tricks to do this, and I highly suggest people look at this. Obviously, you should vectorize everything. FMAs are your friend. And you should definitely not be afraid to talk to performance gurus, right? That's super important. In every supercomputing center, there are a few people who actually understand what the machine does, as distinct from the rest of us, and you have to find out who they are. And despite the fact that they can often be rude and obnoxious, buy them donuts, coffee, whatever it takes. They are the people who you need, okay? All right, so that's so much for performance. Right. The second thing is performance and portability. So again, this is something, assuming you're developing new code, because if you have old code, you're stuck with whatever properties it has, too bad, right? But now there are 3 scales of code development. So one is like individual, so I am free to write my own code because it's my responsibility to maintain it and so on. And then there are the small team, which is a collection of, let's say, smart and opinionated people, which is definitely usually a small team scenario. And then there are a big team to open source. This is more the industrial community code sort of lifestyle. And at the same time, there are issues about how your code actually works. So in the sense that, what is your computer environment? So for instance, it could be low diversity hardware with sort of an individual PI. It could be medium scale where you have a single project, but you run various different science runs or you solve different problems on diverse hardware. It could be large scale where you don't even have one project, but multiple projects, right? Run on a single code framework. using, again, very diverse hardware. So the compute environment that you have to deal with can be very diverse. And this does not refer to problem size. This is, again, one of these sociological things. So you have to ask yourself, which categories does my situation fall in? And that helps you with the portability thing. Because you may not be too concerned about portability here, but you certainly are going to be very concerned about portability here and in this large-scale multiple projects issue, right? Now, the thing is, unfortunately, it is very hard for me to give you any concrete advice on this, because this depends very much on your problem and on your particular situation. But the important thing is to learn from what other people are doing, learn from their mistakes, which there are many, right? And learn also from their successes, which there are definitely a few. And you should adopt and reuse whatever works, and absolutely be ruthless in dumping ideas that don't work. And there are many examples of that. So, don't try and do things that are known to have not worked in the past. They won't work again, okay? So simplicity is extremely useful. So that's something that I've learned, I guess, and I think this is very, very important. Avoiding non-functional adornments is really crucial. The other thing that's important is that software life cycles should be long. I mean, everyone says this, but often they are not. So hardware changes for all practical terms every 3 years. And the supercomputer lifetimes may be 5 to 6 years sometimes, but the rule of thumb is 3, because why? Because the first year, nothing works. And in the final year or so, it's obsolete anyway, so you have a sweet spot of about 3 years in the middle. So keep in mind that if you're going to write a new code for a machine that has a lifetime of 3 years, you should be shot, right? That is really not a smart thing at all. So your code, if it's a complicated code, must have a lifetime of at least a decade. That's how you should be thinking. Or at least the fundamental ideas that have gone in must survive for a decade. There are things in HACC that go back 20 years. Okay, simply because there was some idea that actually is in there in the algorithmic structure of the code. So keep in mind that you have to be very careful about the fact that your code will also evolve over time, because it has a long time, like say a decade, to survive. So it should have a software core that has to evolve. And how it evolves, you have to worry about managing that. So once again, I don't have any great advice, but that's something to keep in mind. So performance and portability are often in opposition, as you can see from these two slides. The question is basically, how do we manage this tension? So let's put all the last lessons together, and along with some other things. So there's this tension. How do you resolve it? So often what happens is, and this is true for as long as I've been in the supercomputing business, is there are always papers on there's going to be this magic compiler or pragma or directive or whatever. You just follow them and everything will be good. This will never happen. So I'm sorry, but it won't happen. There's also this idea that there's this magic programming model that will solve your problem. This will never happen. There's also this idea that special purpose hardware will save the day. This can happen for a finite amount of time, but typically staying with the general purpose world is good. There may be a future for this simply because of the way silicon is proceeding, but for the moment, I would argue that these 3 things are dangerous and you should avoid them. The other question that has come up is obviously this idea of co-design, which is talk to the vendors, see which way their chips are going, see if you can influence them in some way. The problem is that supercomputing is a very, very small piece of an annual $50 billion market. So we are not going to actually influence the chip design a heck of a lot. We might be able to influence it to some degree, and to that degree we can, but it's going to be difficult. So this all is, the fact basically is that you have to follow the architecture. Intel is not going to listen to you beyond a certain point. Know the boundary conditions of what's possible with an architecture, and this is, I think, something very important. As a person writing code, you have to understand the fundamentals of the hardware. What is the chip? What does it do? Why did they design it a certain way, right? What is the bandwidth I can get? What is the latency? These are all things that should be in your head. You don't just think about C++ and stuff like that. This is deliberately why I'm de-emphasizing a language and other data structure issues out here, is because frankly that's a second order thing. Knowing what and how the machine works is much more important. And there's no such thing as a code port nowadays. If you have a code and the architecture of the computer changes completely underneath, and you can find, as the Xeon Phi is a particularly good example of this, yes, your code will run, as one of the earlier speakers said, but it'll be terrible. But that's fine, that's how it is. At least it runs. Now it gives you a chance to improve it, right? So you have to think out of the box, realize that code ports are dead, and get the smartest people you can together, and that's it. I mean, that's basically the only advice I have. So now I switch from this relatively general stuff to tell you a bit more about HACC. So HACC is a code that's written to do precision cosmology, and precision cosmology is something very, very new, as I'll show you a little bit. But it's basically, and so what is cosmology anyway? It's the science of the universe, what makes it, why is it evolving the way it's evolving, how can we use the universe to do fundamental physics, and and many things have happened lately as a result of the advances that have been made in observation, which are also driven more or less by a kind of survey Moore's law, which means that we can now look at very large volumes in the sky, and it's basically follows some sort of Moore's law. The amount of glass on the sky, meaning the amount of telescope area that is on the sky, is not going that fast, but the CCD pixels are going at a very high rate. And for that reason, we can have extremely good sky maps. And from those sky maps, we've learned that the universe is expanding, but not only is it expanding, it's also accelerating. We've learned, as Tom mentioned earlier, that the universe is dominated by a form of matter called dark matter, which we don't know very much about. And we can also learn about things like the masses of neutrinos from these measurements. Just to show you how much the field has come in a very rapid or in a very short period of time, here are a couple of figures. So here is looking at the cosmic microwave background temperature on the sky as a function of angular multiple. And in 1999, you weren't really sure what the heck was happening. There's a lot of data points here. There's a theoretical curve, but you don't really know. Well, here's the same thing in 2013. These are the data points. This is from the Planck satellite. And the solid line is a theory curve that goes through them. It's absolutely amazing how well it works, right? And the same thing is true over here, but this time I'm not looking at the cosmic microwave background. I'm going and looking at the galaxies. So for every galaxy, I basically say, how are the galaxies distributed? I find that they're clustered. That clustering can be characterized by something called the two-point correlation function, and it has a particular shape. And it turns out that at very large scales in 1999, the surveys weren't big enough, so you couldn't measure the correlation function at large scales. But this is the same thing in 2013. That's also 2013. And now the surveys are much, much bigger. And you see this beautiful bump over here. This bump is actually the Fourier transform of that in some sense. Okay? So cosmology has really, really changed, and it's quite amazing. At the same time, we went from 1999 to 2013. We went to a supercomputer that had the performance of one modern GPU. So remember, you couldn't afford a single modern GPU in those days. And now you've gone up by 4 orders of magnitude. So the question is, with 4 orders of magnitude improvement in computing, can we keep up with the experiments? Because the experiments are asking for theory at the sub-percent accuracy. And that's a very difficult task. So you might say, well, there are already codes to do cosmology. Why do we want another one? And so there are many reasons, and some of them I've gone over. And here's an example of, further example of how fast computing is going to grow. And this is just peak petaflops, and this is just my estimate. This is not an official figure. No one should believe that this is official. This is just me. And so things are going to grow. There's going to be a lot more computing, and we have to convert this raw computing power into intelligent software, right? And this is going to be quite difficult because of all of these problems that all of you know about, right? The important point to keep in mind is that this is not new, right? That fact we have more nodes, separate memory spaces, relatively slow networks. This imbalance problem that I mentioned, we already had it in 2008. This is a Roadrunner architecture from 2008, which, as some people might remember, was the first computer to break a petaflop. And it has exactly the same difficulties as we're talking about now. So what is HACC? So HACC is the Hardware Hybrid Accelerated Cosmology Code Framework. And the reason HACC is here is because the other cosmology codes couldn't do what it can do, right? That's the only reason why it exists. And it does very large, high-resolution cosmological simulations. The idea was to run at high performance on all supercomputer architectures at full scale. So high performance is an interesting thing to talk about, simply because people nowadays don't mention actual performance numbers. Usually people talk about scalability. And the reason people don't do that is because the actual performance numbers are embarrassing, right? They run at 1%-ish, sometimes even worse, sometimes few percent. 10% is very, very good. Lattice QCD, for example, runs between 10 and 30%, which is and their codes are highly tuned, and they do a very specific thing. This is not the fault of the people writing the codes. This is basically because the computers are so out of balance, right? But we wanted very high performance levels, and we needed, because we want to run the whole universe. Running the whole universe, as you can imagine, is tricky. And so, well, there's been a lot of success. I'll tell you more about that. But the important point is, so HACC was the first production science code to break 10 petaflops sustained on Sequoia at Livermore. It combines a number of algorithms using a mix and match approach based on a two-level structure. I'll explain why there's a two-level structure, why the portability issue was important in building a two-level structure. It has perfect weak scaling. Its strong scales to better than 100 megabyte per core. That means even on a system that has 100 megabytes per core, the performance doesn't suffer. And it's run the world's largest high-resolution cosmology simulation on Mira and Titan both, right? It was also one of the Coral benchmark codes, and we are ready now for the next machines. It's chosen for early science projects on Cori, Summit, and Theta. So the interesting thing is that when the code was designed, which was somewhere around 2008, 2009 for Roadrunner, I had already guessed what the next generation machines were going to be more or less like, and the code was written for them. And so we have no worries about these systems. It'll be fine. So what exactly does a cosmology simulation code do? Well, it first provides a basic theory of all the cosmological probes. It produces very high fidelity synthetic catalogs, meaning it produces skies that look like the real sky so that people can use it in their observation and analysis. And it's an essential component of analysis toolkits. So I don't have time to explain in detail what these things do. It's too complicated, but I want to just give you quickly a hint of what the equations are. So what we solve is, plasma physicists will be familiar with this, it's something called a Vlasov-Poisson equation, which lives in 6 dimensions. But not only does it live in 6 dimensions, because it has a very interesting property, it has a wrong sign Poisson equation because it's gravity, everything attracts rather than repels. As in a plasma situation, there is an instability, which means even if you start with a very smooth initial condition, you will end up producing structure on very fine scales. So if you actually could put this on a grid, which you cannot because it's in 6 dimensions, n to the 6 is hopeless, but suppose you could, you would find very soon that you cannot run the code because structure forms on subgrid scales and everything breaks down. So the only way that anyone knows how to solve this is to use n-body methods, where you say, all right, I have a 6 dimensional distribution function, and I'm going to think about it as a delta function in x multiplied by some delta function in v. These are the particles, and these are the tracer particles. I dump that assumption in here. I get a bunch of equations. I solve them. That's an n-body code, right? Now, why is it tricky to do this for gravity? It's because there's no shielding in gravity, so you have all the long-range interactions. There's no Debye length. The nice thing about this is the technique is naturally Lagrangian. The particles go wherever they're needed. You don't need any AMR if you're using a particle code. The question is, what are the errors? So I don't have time to talk about that, but that's an interesting point. The other big deal you have to add to all of this, because this is gravity, and gravity is the reason why structure forms, but there's also small-scale physics coming from hydrodynamics, and that's a separate and major topic, and I don't have time today to talk about that. So let's do a very simple calculation and ask ourselves, so how hard is it to do a calculation like this? So in a modern survey, like say the Large Synoptic Survey Telescope, you are going to get something like 10 billion galaxies, right? Now if you say, I want to resolve the inner structure of galaxies or of a dark matter halo that hosts a galaxy, then I should have at least 1,000 simulation particles to do this. So that means the total number of particles I should be running in my simulation is about 10 trillion. And so if you think about it, okay, 10 trillion, 40 bytes, so that's 400 trillion, so that's a lot of, so plus, so that's a lot of memory. So if you're talking about roughly, just to have the particles sitting inside a machine, you can easily eat up half the memory of the full machine. The other interesting thing is the dynamic range, which is the size of the galaxy, roughly speaking, is of the order of 100 kiloparsec or so. This is the mass distribution, not the light. And if you say I need to resolve it, let's say at least by factor 1 in 100, I need a resolution of about a kiloparsec. And a parsec is 3 light years, right? And the universe, when you're looking at it in surveys anyway, is several gigaparsec cube. So you need a dynamic range of 1,000,000 to 1. And the trouble with structure formation in the universe is that structure forms everywhere. I can't use an AMR code where I say, the thing only is interesting here, so I do my gridding over here. Because the structure forms everywhere, it chokes up AMR codes super fast, and they're very inefficient at cosmological simulations. So for all of these reasons, this is a very, very hard problem. I should also mention that the objects form at all kinds of masses, and the ratio of the heaviest object to the lightest object of interest is something like 100,000 to 1, so that's also a big dynamic range in mass. Anyway, it's one of the classic hard problems to solve. And so this is the key motivation for solving this problem. This is why performance is so important in this situation. So in order to deal with this, and I'll quickly go over the principles and we'll go into a bit more detail. So when we built HACC, we decided, okay, we're going to look at all the different numerical methods. We will use a lot of tricky things like mixed precision. We'll worry a lot about data locality, all of this stuff. And there's, so maybe what I should do is, I should actually switch to the next slide and I'll explain things a bit better. So the next slide actually dissects the n-body problem a little bit. So this is the point I was making where you have to think about the physics first. So what the basic idea here is that if you're a particle, you're going to see two kinds of forces. One is a smooth long-range component coming from stuff that's relatively far away from you. And there's a fluctuating short-range component that's a faster time scale and comes from stuff that's closer to you. So this means that you should really be dividing your force calculation into two parts, right? A smoothly varying part and a more sort of fast varying part. So this is basically the hybrid nature of the code. It assumes like grid-like behavior at large scales and non-grid-like behavior at short scales. So there's a smooth field that's produced from taking these n-body particles and producing a density field from it. And that's done on roughly a cube of grid size 10,000 cubes. So it's a fairly big grid. And that gives you 4 orders of dynamic range. We solve a Poisson equation on these scales using a fancy spectral method, which I will explain a little bit. And this is not just solving a Poisson equation, it also does a bunch of other things. Once you've solved the thing on large scales, you also then have to get the small scale forces. And there are different algorithms for doing this, and you have to match the long range and the small scale forces in a way that you get the right answer, which also turns out to be quite tricky. So there's a fair amount of math that goes in here to do this right. But the interesting thing is that the same math that goes in here to do it right also helps you write a much faster algorithm. Okay. So the important point in this algorithm is scale isolation, which is to say it isolates the small scales from the long scales. And the long scales only need to be done much less often because the forces are much slowly varying. And so there's a time stepping scheme that does that as well. So if you think about HACC in pictures, it's something like this. There's a top layer, which is a 3D domain decomposed layer. One of the important things about HACC is that it tries to avoid communication as much as possible in this 3D domain decomposition. So we use something called particle overloading. There's almost no communication across these blocks. And that communication is actually, instead of communicating, we actually compute. So we trade off compute for data motion across these boundaries. There's a nodal layer which consists of short-range solvers, which are actually quite complicated, that lives inside these nodes. So there are entire tree structures that live inside one of these nodal layers. We don't have a global tree because we don't want to communicate. So the basic point is that across this 3D domain, we have very little communication. And inside these, there are very, very efficient solvers that have been written. And let me tell you a bit more about this. So particle overloading is an important idea because it serves two purposes. And one idea is performance, and one is portability. Okay, it's both in the same thing. And the overloading idea simply is that every unit, which could be a rank, let's assume that it's a rank for now, is a rank has a certain number of particles. It has not only the particles that belong to its volume, but it also has a set of particles that are outside it. And a neighboring rank has the same thing. So there are some particles that are intrinsic to this guy, and they don't belong to the other one, but there's a boundary layer in which there are particles that are replicated. So what happens is that the long-range forces are calculated by using only the active particles in each cell. And when you do the short-range calculation in each cell, you also use these passive particles that are out there. But every so often, after several time steps, you basically do a replenish, and you make sure that there is no error due to the fact that you were not really using the fully correct particles from this guy when you were doing your calculation. Now, I know this sounds complicated, and I'm happy to explain it later on if people want to know. But this, it turns out, is a very, very important trick. The advantage of this is that we don't have to do very much of communication at all. And the other neat thing about this is that it completely isolates the short-range solver from the long-range solver. So now let's suppose I have a code that's running on a Xeon Phi, and I want to write a code for, let's say, a GPU. I go to my GPU master and I say, here, this is it. You don't need to worry about anything else, right? This is the little module, that's all I need. It's completely isolated. So that's the two-level paradigm I was talking about. There's this high-level paradigm, which is the grid-based paradigm that handles all of the particle and data motion and everything. And so this is actually, I think, an extremely important point about portability, is you have to make sure that you don't have, when you're taking a code and you're writing it in such a way that only small chunks of the code that are relatively modular, don't talk to each other, have to be changed when the architecture changes. Okay? So the other interesting thing about this advantage of doing it this way is that we have multiple algorithms. So that, in a way, is a test of how well our whole thing works, because we can run one simulation on one machine and a simulation on another machine, and even though the algorithms are different, they should give the same answer. So it's also a test, and they do. So the other important thing about this thing is, which I was telling you, was the spectral solver, which is actually a very significantly important aspect as well. So the long-range forces are smooth, right? And so you have to solve them very accurately, and you have to very accurately then match them to the short-range solver. Because you have a finite number of particles, your force calculations are always noisy. So it's extremely important to be able to, and I don't have time to explain in detail exactly how it works, but you have to have some very special filtering techniques involved. So the point is that if I were to try this using spatial stencils, it would be very complicated and difficult to do, whereas it's very convenient to do this in Fourier space. The downside of this is that you need an FFT, a very large FFT, but that's okay. So we wrote our own. So we have a very fast parallel FFT, and we only need it to run when the long-range solver is run, so that's not too often. And either way, we need something like 4 FFTs for each time step, each long time step, and that's typically tens of seconds, or maybe at worst a minute, depending on how big the grid is. So, and considering that an overall time step can take tens of minutes, this is not a big deal. So by using this Fourier methods very cleverly, you can actually, it turns out you can do all of this matching very accurately. The other interesting thing about this matching is, and so let me explain this matching business. So here is the long-range force between two particles is 1 over r. This is a Newtonian, 1 over r squared, sorry. It's a Newtonian force. And there's a very quiet filtered force that we use. So it's up to about 3 grid units. It's perfectly nice. Looks like 1 over r squared. Then it's not quite 1 over r squared because of this anisotropy noise coming from the particles. But nonetheless, it's much better than if you hadn't done all this fancy filtering that I mentioned. The other cool thing about making it so accurate up to a short distance is that even though this is a residual of the long-range force, this thing is actually very smooth, and I have a very, very accurate expression for it, but it's extremely complicated. And in fact, that expression is this, right? So if you actually wrote this expression out and said to a GPU or Xeon Phi, solve this, boy, it'd be extremely slow, right? Fortunately, because the domain here is so small, you can replace it by a 5th order polynomial, and now you can do anything, right? So this is one of the advantages of being smart, is that you try and make sure that you can do something that in the end the computer likes, right? I mean, I personally, much prefer this, but because I understand exactly where each term comes from, but the fact that I can, not me, but Adrian Pope can write it as a 5th order polynomial, is what's cool and enables me to get very high performance on the blue gene queue. The time stepping uses a symplectic subcycling method, which I don't think I'll explain right now, but it basically is a way of moving the long range and the short range force calculations apart. So how does it all work? So here are the results of HACC on the BGQ. And so I think, as I said, it was the first code to bake 10 petaflops sustained. So this is an example of time per nanosecond per substep per particle. This is a kind of bizarre metric that only n-body people use. But the important thing to keep in mind is it shows perfect scaling. Okay, this blue curve is the scaling, or it doesn't matter which way you look. This is a number of cores, so that's 1 million cores right there. And the way this was run on Sequoia was we were running at full 64 on the BGene queue. So this is a 6.3 million way concurrency test. And this was run at 3.6 trillion particles at 14 petaflops. And this particular test was run at 70% of peak, essentially. And if you look at actual kernel, at the actual force evaluation kernel, it runs about as fast as LinPack. And that is something that Vitaly Morozov, who was our performance guru, wrote, right? So it turns out that by being careful, and you can actually put all the force calculation effort into the force kernel, and the reward is that you get extremely high performance. So now you might say, okay, you guys got lucky with the blue gene Q. What about something completely different? So here's something completely different. So the something completely different is Titan. And the blue gene Q is actually a very balanced machine considering modern machines. It's a relatively cold machine, as I like to call them. This is an extremely hot machine. And on Titan, the memory is primarily host side, right? It's 32 GB on the CPU and only 6 GB on the GPU. And this was against Roadrunner, which was also an accelerated machine that had a balanced memory, 16 GB versus 16 GB. And it turns out you have to think about things like this, because in this particular case in Roadrunner, we put the grid completely on the CPU side, and we put all the particles completely on the GPU side, and then not GPU, on Roadrunner, on the cell, and they never crisscrossed. But here you can't do that. So now you have to worry about data motion that you didn't have to worry about before. So there are various bottlenecks. The important thing is here that all the power is sitting on the GPU. So there's no point making the CPU do any calculation. People say, oh, the CPU can do some serial calculation. That is nonsense, right? The CPU should just sit there and direct data around and basically relax, right? All the work must be done by the GPU. So if you only get a factor of 2 performance improvement by running on an accelerated machine, you wasted your time, right? You must get that order of magnitude. So, and the important way to get that is to understand and control the data motion. And if it's not happening, then really you have to rewrite your code. So, and like I said, once again, this rewriting your code means that just turning on OpenACC is unlikely to give you the performance that you want. So HACC on Titan was a different implementation, right? So what we had to do was push the spatial data to GPU in large blocks and subpartition the data into chaining mesh cubes and compute the force between particles in the cube and neighboring cubes. And we have to do it in such a way that basically you can interleave the communication along with the crunching. And I don't have really time to explain in detail about how it works, but the important thing about this is that this method of doing this also relies on the same idea that worked earlier, which was this idea that we used to do the overloading. So the same overloading principle is used here. And there's a long paper that describes all of this, so you guys can read that. So the important thing with this is that once you do that, you find that, great, the codes work extremely well. Again, I won't explain the details here, but you can get up to 99% parallel efficiency on Titan. The P3M kernel, so this was a different algorithm, ran at 40% of peak, which is about 73% of algorithmic peak, and it was run at around 20 plus petaflops on Titan. So the same problem with changes, with, using the overall framework, but changing things a little bit, you can get extremely high performance. So this is a particular view of portability, and I'm not saying there's a standard view of portability. The standard view of portability is something much more high level, where you're supposed to program to some interface, and everything is taken care of for you, right? Now, it would be great if that was the actual situation, but we are not there yet. So I think we have to be intelligent in designing our code. So now here's finally, I just want to show this movie of the HACC running on Titan. So there's a high resolution Q continuum simulation. I'll start it in a second. This is just the initial condition. So the initial condition is super smooth. And the initial density perturbations in the universe are about parts per million. So it's not surprising if you think this is really smooth, because it is. And this is what is running on one node of the machine. So this code ran on 16,384 nodes. And so you're seeing only 1/16,000th of the simulation. So this Z doesn't matter, just think of it as time. So now the universe starts evolving. And you can see structure forming, right? And just imagine 16,000 more of these guys. That's what the actual simulation is. And so this gives you an idea of the high dynamic range that we need in these simulations and why we had to work so hard to get to this performance. Now, this particular code, this particular simulation is about a week to 2 weeks of machine runtime on 90% of Titan. And things have improved since then. The code is faster because we have an active load balancer that we have improved, and that works extremely well. And load balancing is an important activity, but it's somewhat distinct from the portability and performance issues. So you can see you start with something very smooth, you end up with something like that. Okay. Now, just to summarize, so as I said, thoughtful design of the code infrastructure is super important. Minimizing the number of computational hotspots is really key. Don't create a mess. Make sure that there's just a few places. And sadly, it's often true that in these multi-physics, multi-scale codes, sometimes this is just impossible. In which case, life is tough. But but try to make sure that the number of computational hotspots is as limited as possible. The other issue, and I think this is important, is that sometimes focusing only on the lowest level compute-intensive kernels can be a mistake, because you may be just banging your head against a brick wall, and it may be smarter to step back and say, why am I doing this? So maybe the answer lies elsewhere, right? So one possible solution, that's the one we advocate anyway, is to have a universal layer which has architecture-dependent plugin modules. And the advantage of this is that as long as you can have like a single expert per module, so you're a small team, you can have, okay, Nick Frontieri, who's our GPU person, is just the GPU, and no one else needs to know. Of course, they should know, but they don't need to, and so forth, right? And then the other important thing is that you have to understand the data motion issues in depth. That's really crucial. No amount of language magic is going to solve this problem. If your code is already well designed, minimizes data motion, always hides latency with computation, that's the way to go. This is not magic, but it's important to do this. So you also have to have a code that can change on fast timescales. Well, this is very important because we are always one of the first people to be on some new machine. And new machines are always broken. Nothing runs on them. So if you have to rely on somebody's external libraries, you're dead, right? So HACC, in its main simulation line, uses no external libraries. Everything is hand-coded. And that's because we need to know what we have to do when things don't work, right? This is one of the downsides with this portability scenario, because once you start relying on what other people are doing, when something breaks, it's very hard to fix anything. Moreover, other people have other priorities. So you say, gee, when are you going to put double precision complex here? And they say, well, 6 months from now. So that's one of these difficulties. The other thing that I didn't mention at all is the analysis aspect. So more and more, in the early days, supercomputing was basically solve a very hard technical problem, get me the answer. The answer could be a single number. The answer could be a figure, and you were happy. But now what happens is that supercomputers are becoming actually a data transformation system. You give them a simple equation, and they give you enormous amounts of data back, right? Who ordered this data? But it's there. So now this data analysis becomes a key reason to have the supercomputer in the first place. The supercomputer is only step one, right, in this data transformation. And so this is something like what Tom talked about earlier is becoming an extremely important thing, and that's completely out of the province of this particular talk. But optimizing and making the analysis part portable is another very interesting point. Now, finally, the main HACC paper is here, so all the details of the things that I garbled can be found here. It's also available until September 20 from Elsevier. After that, you have to pay like $35, and I suggest strongly that you do not pay the $35. Send me an email, and I'll send it to you. So yeah, thanks very much.
So going from Mirror to Titan, did you do a complete rewrite, or you still maintain the same code base with
Only one. So basically, okay, so the situation was a little trickier. So, and we are changing it now, but yeah, so initially what happened was the code was written for Roadrunner, and the part that was written for the accelerated component was written in OpenCL. So when we moved to, so obviously the OpenCL component was not there on the BGQ, right? And so, so that particular module was rewritten for Titan, but it was still in OpenCL. So the CPU and the GPU part for the short-range solver was OpenCL, and it runs fine. The downside of this is that, let's just say that there was lack of support for OpenCL, but so we had to do much more than normally we would have. But we have a second version of the code that runs on on Titan, which is written in CUDA in collaboration with NVIDIA using a different algorithm. Right now, our original algorithm is 2 times faster than this other one, but we are still playing around. But it's only this one module. The rest of the code doesn't change.
So was a duplication of work kind of implementing again in CUDA?
So there's always, so there's always going to be this thing, right? Because if you have multiple paths and you decide to take all of them, right? Then the hope is that there are not going to be too many paths, right? But the thing is, look, if I had my own machine, I wouldn't bother. But cosmologists are poor. We do not have our own machine. So we put in the extra work, and that's all there is to it.
What kind of language you use for your code? I mean, you didn't mention.
It's C++. It's C++, MPI plus X, and the X is whatever. So the X can be CUDA, it can be OpenMP, it can be OpenCL. It's whatever is convenient at the lower level. We were thinking of going to assembly, but saner heads prevailed, and we didn't have to do that. So the important thing actually to keep in mind is that on the BGQ, initially Vitaly thought we would have to go to assembly, but we didn't have to. Using just the BGQ intrinsics, the QPX intrinsics, we could get a performance that met essentially lint-pack performance. So this tells you that that you can do a lot of stuff without standing on your head.
So what is your image for the future? You said that 2008 you have a vision for what is going on in the 2013. And so what is your vision now for the future?
It's more of the same for a while. Yeah, if you pay me, I'll tell you more. No, just kidding. Yeah, but for now, I wouldn't worry too much, I would say. For the simple reason that there's going to be a point when the hardware just simply cannot go too far away from the software. And we are pretty close to that. Because you have to ask yourself, why am I running on a machine where I'm only getting 1% of performance? Something's wrong here.
An extension to the question. So in a panel discussion the other day, they said that it will be MPI plus MPI. What do you think about that?
MPI plus open.
MPI. X would be MPI and X would be covered with MPI basically.
No, you mean OpenMP or?
No. MPI plus MPI. MPI would do all the accelerator stuff too inside the zone.
Well, I mean, I'm actually very easygoing about that, right? So I try not to have a religious point of view on these matters for the simple reason that I cannot control it. So whatever works is, I think, the right philosophy. So if someone, so historically, like say some years ago, when the IBM SPs first came out, people said, here's a machine. It was at NERSC. You guys have been doing MPI only. Here's a chance to add some, OpenMP. And we discovered very quickly, no, that slowed everything down. So we said, thank you, but MPI only is just fine. Now, on the Blue Gene Q, also it was said that OpenMP is the way to go. If you're perverse, yes, you can use MPI for everything. But the fact is, you can be perverse. It doesn't hurt you too much. And as MPI gets better, and essentially many things get folded into it, it's quite possible that maybe that's possible to do in the future. So I have nothing against it. I mean, my attitude is fine. If it works better, we'll use it. If not, OpenMP, either way. It's not the end of the world, right? I mean, these are minor decisions. Other things are much more important than, little bits and pieces like that.